Hello everyone. In this video, I'm going to discuss some examples from the Poisson and the hypergeometric distribution. Our quick overview looks like this. We'll start with two easy Poisson distribution examples. These are good practice. The third one is what I would call a difficult Poisson example. You'll see why in a couple of minutes. And then we have an easy hypergeometric, and let's call it a moderate hypergeometric example. Okay, in example one, we suppose there's a certain disease in America which is very rare. Each person has a probability of 1 in 100 million of having this disease. Now let's assume that there are approximately 310 million people in America. That's a fairly good estimate. So our questions are: part A, approximate the probability that nobody in America actually has this disease. And part B, approximate the probability that at most 3 people in America have the disease. Okay, so we first observe that the question is about the number of occurrences, x. In this case, x would be the number of people with this rare disease over a geographic area. So x is a Poisson random variable. Notice that x has to be greater than or equal to 0, but it is not bounded above. So in theory, it could be infinite, but we know that's a little crazy because there's only 310 million people in America. But in theory, the Poisson random variable has no upper bound. The mean is given by lambda. We take the 310 million divided by 100 million, and we get 3.1. Remember, about 1 in 100 million have the disease. So we can now calculate the probability that nobody has the disease. This would be equal to the probability x is equal to 0. Using our Poisson model, we substitute in the parameters. I have e to the minus lambda, and then we have lambda to the x over x factorial, and we could work this out, round off to 3 decimal places. We get a probability of 0.045. Now in part B, we want the probability at most 3 people have the disease. So in mathematical notation, we have the probability x less than or equal to 3. We could express this as a sum. So here I have the sum, x goes from 0 to 3. E to the minus 3.1, right? This is still our e to the minus lambda term. 3.1 to the x over x factorial, right? So if you could visualize this expanded, right, this would have 4 terms to be the sum of 4 terms. The one with x equals 0, x1, x2, and x3. We could work that out and determine that this is equal to 0.6248. So you could do this term by term with a calculator, or you could easily use technology to get this. The easiest thing to do would be to use a CDF. Right, so that's available in both R and in Excel. Also, many other software possibilities. Okay, in the second example, let's suppose that people enter the Flamingo Casino at a rate of 1 every 2 minutes. The Flamingo being a famous casino in Las Vegas. First question, what is the probability that no one enters between 12 and 12:05? Okay, so we think of this 5-minute time period, give a probability to 3 decimal places, and then part B, what's the probability that at least 4 people enter during that time? Now here I would like you to just set up the answer. You do not need to find a final value. So this is a good point to stop the video and try to obtain the answer. Okay, so here's our solution. First of all, we observe that the probability is about the number of occurrences, in this case, arrivals at the casino, and that'll be a random variable x over a period of time. So x is a Poisson random variable. The mean, right now we want to calculate the mean over the 5-minute period. So the mean is 2.5, right? That's the number of customers that enter every 5 minutes. I have to do a little bit of a conversion, but it's easy to see that we get lambda is equal to 2.5. Working out the probability that nobody enters, it's the probability x is equal to 0. Substitute into our formula. We get 2.5 to the 0 over 0 factorial times e to the minus 2.5. You could see this term here just reduces to 1. So we end up with e to the minus 2.5, and easy to see that that's approximately 0.082. Now for part B, we want the probability x is greater than or equal to 4. So the easiest way to do that is to think in terms of the complement, which, by the way, even if you had software, you would have to do this. So we think in terms of 1 minus the probability x is less than or equal to 3. So I have to, break that up into these terms. We could find the answer down here, or at least express the answer as 1 minus e to the negative 2.5, that's p of 0, minus 2.5 times e to the minus 2.5. That would be p of 1, okay? And then you could see here we get 2.5 squared over 2 times e to the minus 2.5 minus 2.5 cubed over 6 e to the minus 2.5. And I said you didn't have to find a final answer, but just in case somebody did, this is approximately equal to 0.242. On to example 3. Okay, so let's suppose the number of times a person contracts a cold in a given year is a Poisson random variable with parameter lambda equals 5. So on average, 5 colds in a year. Okay, so perhaps this person has an issue, they catch a lot of colds, but nevertheless, let's think in terms of this. This lambda is based on a single person catching, on average, 5 colds a year. Now suppose that a new, we'll call it a wonder drug, has just been marketed, and it reduces the parameter to lambda equals 3. Good for 75% of the population. Okay. For the other 25%, the drug has no appreciable effects on colds. Now let's say an individual tries the drug for a year and has 2 colds in that time. How likely is it that the drug is beneficial to them? Okay, so One of the new twists in this example is that we need to use Bayes' theorem to solve this problem. In fact, we need to use Bayes' theorem together with our Poisson probability model. So we want to find the probability the drug is beneficial given this person catches 2 colds. Okay, so according to Bayes' theorem, in our numerator, we get the probability of 2 colds given as beneficial times beneficial, right? This first term is sort of similar to this one, but it's flipped. And then in the denominator, we have probability of 2 colds given as beneficial times the probability of beneficial, right? This term is the same as what we have in the denominator, but then we have to add to this the probability of 2 colds given it's not beneficial times the probability it's not beneficial. Okay, so we know that the probability the wonder drug beneficial is 0.75. That was given. Okay. If we try to work out some of these other terms that we need, the probability of 2 colds given that it's beneficial, okay, so here's where the Poisson comes in. Now, the probability of 2 colds we're going to calculate using the Poisson distribution, and given that it's beneficial, we adjust the lambda to 3. So here's what we get. We get e to the minus 3 times 3 squared over 2. Probability of 2 colds given it's not beneficial. Okay, again, we'll use the Poisson probability model. And now here we have Poisson, x equals 2, lambda is equal to 5. Okay, so that's why I say you notice the different lambda values. Okay, so we work that out over here. Okay, really pointing this out. So this conditional probability is used here, and the conditions are reflected in the different lambda values. Okay, so we can put together our final answer now. The probability that the wonder drug is beneficial, given that there are 2 colds, we can put together just by substituting in these terms. You could see here that this term here in the numerator, same as this term, and then we have to add this other term in. So that completes example 3. Okay, on to example 4. Suppose we have a set of cards that contains 20 cards. So notice it's not the complete deck, it's just a subset of the deck. 6 of the cards are red and 14 are black. Now suppose that 5 cards are drawn without replacements. So you take a card, you don't put it back, you take another card, you don't put it back. We do that 5 times. What's the probability exactly 4 red cards are drawn? Okay, so out of this 5, we're asking what's the probability 4 are red, and we know this information here. In the original 20 cards, 6 are red, 14 are black. So, first observation is we use a hypergeometric distribution. Okay, here we're drawing without replacement, and we have sort of a complete set, but within the complete set there's 2 types of items, the red cards and the black cards. So we let x be the number of red cards. Okay, we know the total number of red cards, we'll use capital M, 6, and the total number of cards is 20, and our subset is size 5, so the probability x is equal to 4. We could think of this in terms of the number of ways to choose 4 red cards out of 6. And the subset we're picking has size 5, so I have to pick one more card, and that one other card comes from the 14 black cards. So this is 14, choose 1, right? We have to do both of these operations, pick red cards and black cards, so this gets multiplied. And in the denominator, it's the total number of subsets of size 5. So you can see with this hypergeometric model, we could either think in terms of the formula, although it's not totally necessary to have a formula. We could sort of reason this out from basic probability principles. Another thing you could do with this is if you wanted to check this, you could use R. The probability function in R would look something like this: D hyper XM capital N and R lowercase n. Okay, finally, example 5. This may be one that you want to try to do on your own. Suppose the AMS 311 exam will test students on some of the 50 key facts about probability. Student Bob studies 15 of these facts, and let's say the instructor will randomly pick 10 of the 50 facts to put on the exam. Let's let X be the number of the AMS 311 facts appearing on the exam that Bob has studied. Question is, first, what's the distribution of X? And part B, what's the probability that out of 10 facts chosen by the instructor, Bob has studied 8 of them? And then finally, what's the variance of X? So again, I didn't write it here, but this would be a good problem to stop the video and try to get the answer on your own. Okay, so we begin with part A, and you probably realize that X is a hypergeometric random variable, right? We're picking from a set, and within the set there are 2 types of questions. Here it's questions that Bob has studied versus questions he has not studied. Okay, so we know the exam has 10 questions, so that will be our subset. So our lowercase n is 10. Okay, the complete set has 50, and there are 15 questions there. So this represents the 15 that Bob has studied. All right, so we have the probability, our random variable X is equal to X. So this is just the general form for this problem. It's 15 choose X times 35 choose 10 minus X over 50 choose 10. For X equals 8, we get 15 choose 8 times 35 choose 2 over 50 choose 10. And we could work this out. You see, we get 0.0004. So a very low probability. The last part is simply to find the variance for X. So here we want the variance for a hypergeometric random variable. Here's your general formula. N times the fraction m over capital N. So we get 10 times 15 over 30. You could see that this will, easy to see this answer. Just divide 10 into 50, goes 5 times, so I get 15 over 5, which is 3. So this completes the video. I hope you enjoyed it.